Okay, so now we're going to switch gears a little bit, and we're going to look at finding the area of an inscribed rectangle. There are two cases. There's one that, like the picture you see up here, where it's inscribed under one curve between the x-axis and a function, and then there's the other case down here where the rectangle is inscribed between two curves. So let's look at number 4 first, and then we'll move on to the next one. Okay, so we've got a picture here, and we have some rectangle, like so, where the upper vertices are touching the function, okay, and the function is y is equal to 6 minus x squared. And what do we want to find? We want to find the maximum possible area of the rectangle, because you know, you could have a, I don't know, well, this is a terrible picture, but this rectangle, or you could have a narrower rectangle, or you could have one this way, right, and so forth. So anyway, we want to find the maximum possible area. Well, since I'm looking for area, I'm automatically going to relate that to a geometric formula, which is length times width. So what we don't know is this distance here from the origin to this vertex, and so we call it x. And by symmetry, we call this one x as well. So this length here is 2x. And the height, if it's just one function, the height will always be the height of the function, or the width of this rectangle, because the vertex touches it. It's the distance from the x-axis to a point on the curve, and so the width of this is going to be 6 minus x squared. So my area formula is going to be 2x times 6 minus x squared. And I'm going to clean that up a little bit. So a of x is equal to 12x minus 2x cubed. Why? Because I'm going to take a derivative and I want it to be nice and easy. Okay, so that being said, now I have to find the domain. So I have a function, I have to find the domain. Well, I could have a rectangle where maybe the width is 0, right? So it might look, so here's my curve, it might look like this, right? So I'm going to start at 0 for my domain, and where am I going to end? Well, how I figure that out is I take my function and set it equal to 0 and solve. So, you know, 6 minus x squared is equal to 0. So x squared is equal to 6, making x equal to plus or minus root 6. Now I can discard negative root 6 because I can't have a negative width. So, and x is equal to positive root 6 is where this thing is going to end. So that's going to be my upper bound. Now I can go ahead with what I know. I know that if I take the derivative of this function, I'm going to have 12 minus 6x squared. And if I set that equal to 0 and solve, I'm going to subtract 12 from both sides, right, and divide by 6. So I have x squared is equal to 2. So x is plus or minus root 2. And again, my critical numbers, you know, I have negative root 2 and positive root 2, but I can discard this one because this one is not in this interval. Alright, so I have this critical number here and the two endpoints, and so now I have to evaluate the function at each one. Well, so let me just rewrite it here again in case it goes out of view. If I evaluate a of 0, well, that's 0. If I evaluate a of root 6, well, that's 12 root 6 minus 2 times root 6 cubed, right? And that's 0 as well. And so probably it's going to happen at root 2. And let's see, that's 12 root 2 minus 2 times root 2 cubed, which is 12 root 2 minus 2 times, so you know, the square root of 2 cubed is the same as the square root of 8, right? And the square root of 8 is 4 times 2, so it's 2 times 2 root 2. So we have 12 root 2 minus 4 root 2, or 8 root 2, like so. Alright, so anyway, the maximum area for this rectangle is going to be 8 root 2. And that's going to happen when our x value, or our length there, is the square root of 2. Let's do the other one. This one's pretty straightforward. So is this one really. It's just there's a little bit more to do here, and finding the domain on this one is going to be a little bit of fun, and I say that facetiously. Okay, so we have two curves. So I'm going to do them like so. And we've got our rectangle in here with vertices, upper vertices, vertices, lower vertices on the lower curve and upper vertices on the upper curve. So this thing here, right? Now, the rectangle is inscribed between the graphs of 4 minus x squared. Well, that's the frowning function, so that's this one. And the smiling function, 1/4 x to the 4th minus 1. And what do we want to do? We want to find the width of the rectangle that has the largest area. So we want to maximize area. And our area formula geometrically, we know is length times width. Well, just like in the last problem, I'm going to let this distance be x, so this one is x by symmetry, and so this is 2x. The height of this thing is just top curve minus bottom curve, right, or the width. So it's 1/4 x to the 4th minus 1 minus 4 minus x squared. Okay, this is going to represent our width, which is 1/4 x to the 4th minus 1 minus 4 plus x squared. So plus x squared minus 5, right? So that's our width. So our area function then is going to be 2x times 1/4 x to the 4th plus x squared minus 5. And if I clean that up a little bit more for my derivative, that's going to give me what, 1/2 x to the 5th plus 2x cubed minus 10x. There's my function. Okay, now I said the domain was going to be a little bit of fun, and it is. When you have a rectangle inscribed between two curves, how you find the domain is you set the two functions equal to each other. So let's do that. We have 1/4 x to the 4th minus 1 equals 4 minus x squared. And I'm going to multiply through by 4 to get rid of the fraction. So we have x to the 4th minus 4 is equal to 16 minus 4x squared. That gives me x to the 4th plus 4x squared minus 20 is equal to 0. And wah, 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 it's not factorable. So we have to use the quadratic formula. Alright, so this is what I'm going to do. I'm going to treat, I'm going to let u equal x squared. So I've got u squared plus 4u minus 20 equals 0. Now that's going to be my ABC. That's going to go in. It didn't change anything, but I just want to show you. Alright, so anyway, we got -4 plus or minus the square root of 16 minus 4 times a times c over 2 times a. That's going to be -4 plus or minus 16 plus 80 over 2, which is -4 plus or minus 96 over 2, and I think 96 is divisible by 16, but let me double check. Yeah. This is -4 plus or minus 4 root 6 over 2. So 16 times 6 is 96. So I just pulled the 4 out. And this is equal to -2 plus or minus 2 root 6. So what I have is x squared equals -2 plus or minus 2 root 6. So that means x is equal to plus or minus -2 plus 2 root 6, plus or minus 2 root 6. Alright, so you can forget about the minus here on the outside, But let's look and see what that equals. So negative 2 plus 2 root 6. Okay, so this is bad on my part because I'm rounding. 2.89898. So it goes on further than that. You shouldn't round, but we should get close enough. Just don't do that on the AP exam. All right, and if I take the square root of that, I get that x is approximately 1.702. Right. The other thing is that if I do the minus, so I did the plus of this thing. If I do the minus underneath the radical, I'll do that over to the side. I'm going to have negative 2 minus 2 root 6. That's going to give me a negative under the radical, right? Error. So you can discard that. So this is my critical number. Sorry, not my critical number. It's not my critical number. It's the endpoint of my domain. Why? Well, because the domain goes again from 0 to that point of intersection, 1.702. So I have a function and I have a domain, and now thankfully I can take the derivative. So let's see if I can do it in this space over here. See what happens. Okay, so a prime of x is going to be 5/2 x to the 4th plus 6x squared minus 10. Now I've got to set that thing equal to 0 and solve to see if there's a critical number in between this and this. By the way, oops, I want to go back. Well, let me go back. Yeah, so look what I did. This is what I wrote. I wrote 1.702. It should be 1.703. So I'm going to change that to a 3. Okay, so anyway, here's my derivative. I have to set that equal to 0 and solve. And again, that's not anything that's pretty at all to solve. We're going to have to use quadratic formula again. Right, and again, I'm going to let u equal x squared, so what I'm really dealing with is 5/2 u squared plus 6u minus 10. So we've got negative 6 plus or minus, so you know, x squared equals, right, instead of x equals, it would be x squared equals negative 6 plus or minus the square root of 36 minus 4 times 5/2 times negative 10 all over 2 times 5/2, or 5. I'm not going to have enough room in my little box. So that's going to be negative 6 plus or minus. We have 34. And this is going to become a positive. So I've got, I can cancel, or I can divide a 2 into itself here and 2 in here. So I've got 10 times 10 is 100 over 5. So that'd be what, 134. And let's see here. Oop. Something's weird. 36. Sorry, this will be 136, right? So 10 times 10 is 100 plus 36 is 136. So yeah, 136 would be 4 times 34. So let's just get a new piece of paper here. Going down here. So I've got negative 6 plus or minus. 136 is 4 times 34. So this would be 2 root 34 over 5. I can't divide anything in, so I'm just going to say x equals, right, the positive square root of this little nightmare here. Wow, this is ugly. -6 plus or minus 2 root 34 over 5. Yeah, awful. And let me put that into my calculator. So we've got the square root. Actually, I'm gonna do the square root next. So we've got -6 plus 2 root 34. I'm going to use parentheses because I don't trust this thing. Divided by 5. I'm going to do second radical, second answer. So I get x is approximately 1.06413. So again, I'm rounding. And there it is. It's really hard to see on the calculator. 1.06413. That's what I'm rounding to. So that's my critical number. And so now, right, I've taken my derivative and I'm going to test 0, 1.703, and this critical number in the original function, which is this thing right here. Well, if I plug the 0 in, that's nice. I get a 0. If I plug in 1.06413, well, just bear with me. Oops, 06413. Okay, I get approximately 7.549. And then finally, if I plug in 1.703, I'm going to get 0. So, what can I say? I can say that the maximum area is going to be 7.549. And that's going to occur when x is equal to 1.064 blah blah blah. Okay, I hope that makes sense. So that's the inscribed rectangle. That's another type of problem that you could see as part of or solely as a maximization, optimization type problem. I'll find some examples. What I can tell you that I know is this, is that generally these are on the multiple choice. Things have changed now where who knows what's going to be on this little 25-minute FRQ. So, you know, I'm thinking they could easily put something like this. They could work something in for sure. It's not like an issue. But generally you wouldn't see this type of a problem except in multiple choice. So don't blow it off. Know how to do it. I'll find some extra examples and I'll post them for you to play around with after you finish watching the videos today, which will be tomorrow your time, because right now it's 4:56 p.m. on the 13th of April. So you'll be viewing these tomorrow on the 14th. All right? Have a good day.